Okay, then let's move on to third type of problems, which is basically this one, this type. Okay, now third type of problems are actually the most important ones, because in economics most of the times you have non-negativity constraints. You also have some inequality constraint, like the budget constraint. Okay, so if it's a cost minimization problem, then you have the constraint on, let's say, you want to produce at least some level of output. So how do you actually solve the problems involving inequality constraints? Okay, so what I'll do is this, first of all, let me just remove this. Okay, and then I'll add this, with more constraints. So first of all, let me just write the conditions, the necessary condition for maximizing fxy with this, subject to just one inequality constraint. And then I'll tell you how to write this for multiple inequality constraint, because in economics you see there are other inequality constraints as well, like x is non-negative, y is non-negative. Okay, so first of all, let's see how to write the necessary conditions for solution to this problem. Okay, so again, you're going to write the Lagrangian in exactly this way. Okay, there is no difference. You're going to write the Lagrangian in exactly this way. Okay, is that clear? Okay, and now earlier, the set of necessary conditions in this case was known as Lagrangian conditions. In this case, we are going to call them Kuhn-Tucker conditions. Kuhn-Tucker conditions. Kuhn-Tucker conditions. Okay, so what are the Kuhn-Tucker conditions? Okay, so let me just tell you those Kuhn-Tucker conditions. So the first Kuhn-Tucker condition is exactly the same as before. Okay, so it is del L by del X is 0. Okay, so if you just take the partial derivative of this with respect to x, that should be 0. And the second Kuhn-Tucker condition is del L by del Y is 0. This is again the same. The only difference will be the third condition. So if you remember in the previous case, the third condition was just the constraint gxy equal to c. In this case, it will not be just a constraint, it will also be some other condition. Okay, so it will be basically this: gxy less than or equal to c. That's one condition. Second condition is lambda must be greater than or equal to 0. Okay, and the third condition is the product of these two must be 0. So lambda into gxy minus c must be 0. Okay, so these are known as Kuhn-Tucker conditions. Okay, so these are the necessary conditions for the optimum. Okay, and if the Lagrangian function is concave, okay, so in concave in xy, then these are also sufficient conditions. Okay, is that clear? Okay, now let us look at the second type of problem. So suppose you want to maximize fxy with respect to xy subject to gxy less than or equal to c. X is non-negative, y is non-negative. Okay, so how do you write the Lagrangian function for this? Lxy equals fxy, okay, minus lambda gxy minus c, right? Okay, now you have two more constraints. So what you're going to do is just add two more terms. Like for example, you have added this term for this constraint. Similarly, you're going to add two more terms for these two constraints. Okay, so I'll use, so I'll not be using lambda. Let me use some other Greek letter, mu. Okay, let me use mu. Okay, so always, you have to convert it into this form. So how do you convert this into this form? You can just write minus x less than or equal to 0. Okay, and then just take this to the other side. It's 0, so it's the same thing, and then multiplied by minus mu x. So minus mu, let me put a subscript here so that I know that this is a multiplier associated with x. Okay, into minus x. Okay, so if you want, you can just ignore these minuses, okay, and then write it as plus mu xx, okay, and similarly plus mu yy. Okay, so this is a Lagrangian function. Okay, and then what are the Lagrangian Kuhn-Tucker conditions? Okay, so these are the Kuhn-Tucker conditions, KT conditions, the necessary conditions for the optimum. Okay, so the first is del L by del X is equal to 0. Okay, second is del L by del Y equal to 0. Okay, then third is basically so third is basically associated with this constraint that gxy must be less than or equal to c. Okay, because that's a constraint, right? And then lambda must be greater than or equal to 0, and then lambda times gxy minus c is 0. Okay, and then you also have three inequality constraints associated with this one. So you have x is non-negative, mu x is non-negative, okay, and then finally x times mu x must be 0. Okay, and then you also have something similar for this one. Y is non-negative, mu y is non-negative, and then mu y times y must be 0. Is that okay? Okay, so these are the KT conditions. So it turns out that these are the necessary conditions for solution to this this optimization problem. And if Lagrangian function turns out to be concave as well, okay, then these become sufficient conditions. Okay. Okay, great. By the way, this will also give you corner solution. So let's solve this problem. Okay, so suppose you want to maximize 2 root x plus y. Okay, and let's say the budget constraint is x plus y less than or equal to 1. Okay, x is non-negative and y is non-negative. Okay, so you want to solve this problem. Okay, so what is the Lagrangian function? Lxy equals 2 root x plus y minus lambda. Take this to the other side, you're going to get x plus y minus 1. Okay, and then you also have plus mu xx plus mu yy. Okay, so obviously you can also solve this problem using other methods that you already know. You can use the graphical method if you wish. Okay, but this is another way in which you can do it. Okay, so let's solve this. So what are the Kuhn-Tucker conditions for this problem? These are the Kuhn-Tucker conditions. So let's write these conditions. What is the first condition? That del L by del X is 0. So can you tell me what is del L by del X? Anybody? 1 by root x, right?
Minus lambda plus mu x.
Minus lambda plus mu x, right? Is equal to 0. What about del L by del Y? It is 1 minus lambda
plus mu y.
Very good. Okay, that's right. Let's do the next one. So we are going to write these 9 inequality, well, 6 inequalities and 3 equalities. Okay, so what are these? Well, x plus y must be less than or equal to 1. Okay, lambda must be greater than or equal to 0. Okay, and then this must be 0. Okay, so x plus y is less than or equal to 1. Lambda is greater than or equal to 0. Lambda times x plus y minus 1 is 0. Okay, the next is x is non-negative, mu x is non-negative. Okay, and then this is 0, right? Mu x times x is 0, and then you have y is non-negative, mu y is non-negative, and mu I times y is 0. Okay, so we have to solve the system. Okay, but first let's just check if the Lagrangian function is concave or not. Okay, is this concave? Notice that 2 root x is a concave function, y is a concave function. By domain extension and some theorem, this is a concave function. Of course, because differentiable, you can also use twice differentiable, so you can also use the other method, that I just told you today. Okay, and then this is linear in x and y, so this is also concave. This is linear in x, this is linear in y, this is also concave. So the entire Lagrangian function is concave. Is that okay? This is the sum of concave functions. Yes or no? Okay, so basically, whatever is going to solve this problem is also the solution to the optimization problem. Okay, is that clear? So we just have to solve the system, okay, and then we'll get the solution. Okay, so how do we solve the system? Okay, so if you see, we have to actually deal with these inequalities. Okay, we can take cases. Okay, because there are two possibilities here, right? Y can be strictly greater than 0 or 0. X can be strictly greater than 0 or 0. X plus y can be strictly less than 1 or equal to 1. So if you see, there are two possibilities for this, two possibilities for this, two possibilities for this. So 2 into 2 into 2, 8 possibilities we have to check. Is that okay? Yes, we have to check for 8 possibilities. Solution might be anywhere in those eight possibilities. So what we can do is we can start with this case. Suppose x plus y is strictly less than 1. Okay, so notice that when I'm checking for x plus y strictly less than 1 without imposing any restriction on these, okay, I'm actually dealing with 4 possibilities at the same time. Because half of the possibilities will involve x plus y less than 1, half of the possibilities will involve x plus y equal to 1. Okay, so now if you see x plus y less than 1, if you just start with this, x plus y less than 1 would mean that this product must be 0, because if x plus y is strictly less than 1, okay, and lambda times this is 0, so this means that lambda must be 0. Do you agree?
Yes, Professor.
Okay, now if lambda is 0, you put a 0 over here. What is the value of mu I you're going to get?
-1.
-1. Now is that going to contradict this?
Yes.
Yes.
Okay, so this means we have ruled out 4 possibilities, 4 cases. So there is no solution to this system in the situation where x plus y is less than 1. So we've ruled this out. Yes? Okay. So 4 cases are gone. So we are left with just 4 cases now. X plus y equal to 1 must be the case, because x plus y less than 1 is not possible in a solution. So x plus y equal to 1 must be the case. Now there are 4 possibilities. Okay, first possibility is x is positive and y is positive. That's one possibility. Second possibility is x is positive and y is 0. Okay, third possibility is x is 0 and y is positive. And fourth possibility is x is 0 and y is 0. These are the 4 cases that are left. Now, can you tell me which of these 4 cases I can remove straight away? Obviously, x is 0, y is 0, right? I mean, x plus y equal to 1 and x and y both are 0. That's not possible. Okay, so this case is ruled out straight away. So we just have to check 3 cases now. Okay, I mean, just to figure out where the solution is, we just have to check these 3 cases. Is that okay? So let's start with this one. Okay, let's start with this one. So x is positive, y is positive. So if x is positive, y is positive, do you agree mu x and mu y must be 0? Do you agree? Because if both x and y are strictly positive and this product is 0, so mu x must be 0 as well as mu y must be 0. Yes or no? Yes or no?
Why is mu x 0 when x is positive?
Because if x is strictly positive and this product is 0, so the only way this product can be 0 is if mu x is 0, right?
Right.
Okay, similarly mu I must be 0. Okay, so if mu x and mu I are 0, then lambda is actually 1 by root x. Okay, and lambda is also 1, right? So if you equate them, you'll get x equal to 1. Okay, and that's going to give you y equal to 0. Okay, is that fine? So which is inconsistent with this case? Do you agree?
Yeah, y should be greater than 0.
Yeah, so this is inconsistent, so there is no solution in this situation, right? So we can ignore this case. Okay, this case is ruled out. So now there are just two cases left. One is x is positive, y is 0. The other is x is 0, y is positive. Okay, now if you look at this one, okay, let's start with this one first. Okay, x is 0, y is positive. So if x is 0, y is positive, then well, y is strictly positive, so mu I must be 0. Okay, if mu I is 0, then lambda must be 1. Okay, if lambda is 1, okay, and x is 0, do you agree that mu x is going to be negative infinity? Yes or no?
Yes.
Okay, so again, this is inconsistent with this. Yes, so this case is also ruled out. So we are just left with one case, which is x is positive, y is 0. And if x is positive, y is 0, then x must be 1, y must be 0. Okay, now we can quickly check, what are the corresponding values of lambda, mu x, and mu y. So what is lambda, mu x, and mu y? Well, x is 1, y is 0. So if x is 1, then mu x must be 0. Okay, and if mu x is 0, then lambda must be 1 by root x. So lambda must be 1. Okay, and if lambda is 1, then mu I must be 0. Is that okay? Just check this. Okay, I mean, just check that this is a solution to the optimization problem. You can try the alternative method, you'll get the same thing. Is that fine?
Yeah, so this is the only solution, right?
Yeah, this is the only solution. Okay, have you all understood this? Okay then, so I guess we can stop here for today. So